This pumping engine is a giant among engines. It's one of the biggest in the world. Did the Victorians really need to go this big? Or were they just power crazy?
At first sight, the Industrial Revolution seems to have spawned some monstrous machines.
Big, isn't it?
The truth is, the Victorians built big to solve big problems.
In the 1820s, the Industrial Revolution was in full swing, and Britain's cities were getting bigger and better. The only problem when you start bringing that many people together is that you need fresh water, and lots of it.
Providing fresh water to the new industrial cities was going to be a big challenge.
The problem was particularly bad in London, but the Grand Junction Canal Company had a good idea. Why not use the canal not just for transporting goods, but also as a water supply? So, in 1811, they built a steam-powered pumping engine here at Paddington to supply drinking water. Today, the water's pretty clean, but in the 19th century, it wouldn't have been. The problem was sewage, raw sewage. With low population levels, streams and watercourses can keep pace, they can flush it away, and you can still use them for drinking water. But with the rapidly expanding population centres in the 19th century, this would have been a cesspit.
As cartoons of the time illustrate, one glass of water might contain 20 organisms visible to the eye and a host of bacteria. It could literally be death to drink it.
So, people drank beer. The brewing process sterilises water, so that in the 1820s, Londoners alone were drinking 4 times more beer than the whole country does now.
By 1820, the water was so dirty in Paddington that the pumping station was shut and operations moved to Chelsea. Clean, fresh water from the fast-running Thames, and plenty of it.
In your dreams, here's a quote from 1829. The accumulation of waste and dead animals, blood and offal from the abattoirs, the outpourings from gasworks, dye works, glue works, bone works, tanneries, distilleries, breweries, chemical and other works, all thoroughly stirred up by the unceasing splash of 298 steamboats. Not a pretty sight, and not a pretty smell. In a last-ditch attempt to provide clean water, the Grand Junction Canal Carrying Company moved further upriver. In 1838, they came here, Kew Pumping Station. And this is the engine that first pumped the water. The most famous brand name of the Industrial Revolution, a Boulton and Watt engine built in 1820, the year of Watt's death. And it was still working in 1944. It's a big, powerful engine. It can lift 590 litres of water per stroke. If it was a car, the tax would be calculated on an engine size of 3,080 litres. The diameter of the cylinder is 1.6 metres wide, 64 inches. But that's nothing compared to this. This has a cylinder diameter of 2.2 metres. It is the Grand Junction 90-inch. It is a big engine.
The 90-inch was designed to solve a big problem for Kew Pumping Station. London's population had more than doubled between 1800 and 1850. So had the demand for water.
This magnificent engine represents the absolute zenith of 19th century craftsmanship and engineering skill. Built in 1846, it was the largest waterworks engine in the world. The component parts are massive. The beam alone weighs 32 tons. But why build so big?
It's all about pressure. Nobody had found a way of using steam at high pressure with big loads. So to pump more water to London's ever-expanding population, the only option was good old £40 per square inch, but build bigger.
This 90-inch monster works at the same steam pressure as the 64-inch Bolton & Watt, no mean engine itself. So, if you want to increase the power, you increase the cylinder size. So this engine could lift 3 times the Bolton & Watt's capacity. So at the height of its working life, this was lifting 7.5 million gallons a day. And with the aid of Richard here, who's the driver, we're going to see how it worked. Take her away, Richard. He has to work the engine's valves manually at first, and then hopefully she will then work automatically. This is a Cornish engine built by Harveys of Hale. They sent their engines all over the world, and one of the things they always sent with them was a driver, usually a Cornishman. You Cornish, Richard?
No, from London.
He's a Londoner, so that's all right. Do you give them human character, or do you see them as machines? Or
No, each one has an individual character, and they behave differently from week to week.
And what's this one like?
Can be a bit of a nightmare when she wants to do.
She's a bit stroppy, this one. I'm not surprised the amount of work she has to do. Come round here and you get a sense of why this is such a big engine. Because that is what it was lifting.
At full capacity, the engines of the Kew Bridge station were capable of pumping 30 million gallons. That's 115 million litres of water a day. Over 100 people were employed on the site, and as late as 1938, the station was fully operational. These engines were built big and built to last.
So, how do you get a massive engine like this into a building? It looks like you build a building round it, but actually the opposite is the case, because the structure itself is part of the machine. This bears the weight of the beam, 32 tons, which was hoisted into place on these cast iron columns. And these massive cast iron pillars have Doric capitals. The whole building is full of light. It was designed to be like that, so you didn't need artificial light. It wasn't any electricity. The whole building is incredibly practical and beautiful. It's a cathedral to steam. We now have the capacity to move water, but we still need to clean it. And I shall now demonstrate the sand bed filtration system, which is still the basis of water cleaning today, but was first used in 1829. As this is a filter, it has a hole in it. You've also got to imagine that this is a vast basin. I'm using a bucket. Stones, acting as the lower layer, much in the same way as you drain a flower pot. And then some gravel. Some filtration systems also used charcoal, but the principle's the same. And on top of that, sand. So, we've basically assembled a filter. And this should come out looking a lot better than when it went in. But there was also another significant development, because it was discovered during the cholera epidemics of 1849 and 1853 that outbreaks were reduced in areas that were supplied with filtered water. But it was only in the 1860s, when the science of bacteriology was developed, that it was discovered that filtration removed up to 98% of bacteria. Not bad. Smells all right as well.
So why not stop sewage getting into rivers and streams in the first place? By the early 19th century, big steam engines were being used to provide fresh water for the new industrial cities. Why not use the same technology to get rid of sewage?
And that is why this is here. This is the South Bank in London. It's not just a fashionable promenade. This is the line of a main sewer, part of Sir Joseph Bazalgette's 1853 plan to sort out London sewage problems by building two huge trunk sewers. There's one here on the South Bank and one on the North Bank.
Yet again, it was a big and courageous undertaking. Sewage would run down two halves of a main drain to treatment plants in the east of London. There it will be stored till high tide and then released into the river.
Gravity does most of the work, and it ends up here, in the East End, as far away from the Victorian city as the engineers could manage. But by the time it gets here, it's 30 feet below us, and it has to be raised into a 25 million gallon reservoir. And this is what does it. This is a giant plunger. It is the largest pump I have ever stood in, and it could handle 140 tons per minute. And there were 4 of them. And these are what drove the pumps. These 4 sleeping giants are the most massive rotary beam engines in the world. And this is another cathedral of steam. Amen.
London was the first capital city in the world to have its sewage pumped out to sea. And there's no doubt the Crossness pumping station was designed to impress visiting dignitaries. It's built in a Romanesque style and contains some of the most beautiful decorative ironwork you'll see anywhere in the world. But it's practical too. The cast iron floors have holes woven into them to allow heat from the ground floor boilers to disperse.
These engines all have names. Princess Alexandra, Albert Edward, Prince of Wales, Albert, Prince Consort, and behind me, Victoria, Her Majesty the Queen. Because in 1865, the royal family were proud for their names to be associated with the pumping of raw sewage. And in 1900, these steam royalty were converted to triple expansion engines to provide more power.
The engines at Crossness are currently undergoing restoration, but this is in perfect condition. A triple expansion waterworks engine built in Leeds in 1910, a steam engine at the peak of development. Advanced boiler and engine technology to work with high pressure steam.
Improvements in boiler specification meant that steam could be used at 200 pounds per square inch instead of boring old 40 pounds per square inch. Up here you can see why it's called a triple expansion engine. The steam at high pressure, 200 pounds per square inch, enters the high pressure cylinder. And then, after doing its work, it's still at high pressure, 80 pounds per square inch. So, it then passes via these coreless valves, worked by tappets, which I like very much, into the intermediate pressure cylinder. It's then still at 40 pounds per square inch, and the last amount of energy is extracted from the low pressure cylinder here. It's very, very efficient and very satisfying.
Finding more efficient ways of creating power was key to maintaining the momentum of the Industrial Revolution. And towards the end of the 19th century, a new form of power appeared. Most people first saw it in what might seem an unlikely place to find cutting-edge technology: the fun fair.
Look at this! It's beautiful, isn't it? This is a showman's engine. That's why I've got this fantastic barley sugar twisting here. It's actually, basically, an agricultural engine, but it's been adapted because those showmen knew what they were doing. For the first time, they had a huge class of people with money and leisure time, and they wanted attractions, and this drove them. These engines pulled the fairs from town to town. They provided the power to erect the fairs and the power to run the rides. And they also provided something else. In the late 19th century, these fairs were big business. And these showmen were always looking for a new attraction. And this was it, ladies and gentlemen. Electricity. It was the newest thing. This engine's got a great big belt-driven dynamo bolted on the front to generate this new electricity. Imagine what it must have been like. You lived in your house that was lit by gas. So was your work. It was dim, it was flickering, it smelt. This was new. Everything came on at once and didn't flicker. So this new power source, the power source of the 20th century, was produced by 19th century steam technology, a beautifully adaptable machine. And they were so proud of these engines and so proud of their technology that they gave them pride of place at the fair.
Canal companies were constantly looking for ways to increase their efficiency. How could they exploit this new power, electricity?
In the last quarter of the 19th century, British industry was at full stretch, and canals were still vital for the carriage of goods and raw materials, so they were still at the cutting edge of technology. And in 1875, they came up with this. The Anderton boat lift, the cathedral of the waterways.
The lift was one of the first places electricity was seen on the canals. It was built to take cargo boats 15 metres between the River Weaver and the Trent and Mersey Canal. The designer, Edwin Clark, used a revolutionary system of hydraulics.
And this is how it works. It's quite simple. There are two tanks, or caissons, that work like that, filled with water that could take two boats. Originally, a steam engine pumped river water under pressure into the rams that were underneath them to lift them like that.
Operations were made easier by there being slightly more water in the top tank, so gravity could help the hydraulic rams raise the lower tank.
The problem with the river water was that it was so badly polluted that it actually corroded the rams themselves. So in 1908, they stuck a whole new bit on top, which lifted the caissons by electricity.
Come the early 1900s, new engine technology would also help the canals become quicker and more efficient.
Beautiful, isn't it? It's a Bollinger engine, first installed by Cadbury's in their boats in 1911.
No electric coil yet. You've got to get the fuel plug red hot before the fuel will ignite.
this is an internal combustion engine. The fuel source, in this case diesel oil, is ignited inside the cylinder. Not the easiest things in the world to start.
With their new engines, boats could now move much faster. But would he be fast enough?
Most people think that it was the railways that killed canal transport, but it wasn't, it was the roads. After the First World War, in 1918, huge numbers of army lorries were made available, all powered by internal combustion engines. And they could carry loads quicker and from door to door. That's it for the canals, isn't it? No more great engineering achievements, just a sad decline into senility. You could not be more wrong. Look at this, the Falkirk wheel.
With more and more people taking boating holidays, the canals are back in business big time. The Falkirk wheel is a match for any of the great Victorian structures. The canal has been restored between Glasgow and Edinburgh, and the wheel replaces a flight of 19th century locks. Just like the Anderton boat lift, it's a counterbalance system. The weight of the descending tank is used to help raise the ascending one. Boats are carried 35 metres, that's the equivalent in height of 8 double-decker buses.
$1,000 tons of steel, 1,200 tons of prefabricated steel, nearly 15,000 bolts, 35 square metres of canal lining, 7,000 cubic metres of concrete. Big, isn't it? Big, isn't it? The Falkirk wheel is like many of the big structures of the Industrial Revolution. It's big and it does its job supremely well. Big, beautiful, practical. Perhaps we haven't forgotten how to do it after all. Beautiful wooden boats, these, because you can't make wood square. So underneath the swim, it's beautifully shaped, it cuts through the water. It's lovely to steer.